Hi folks, Mr. Ackerman here. Thanks for watching. Today we're starting a new unit, so this is the first video of unit number 2. It's for lesson number 1. The topic is forces, free body diagrams, and Newton's laws, which you did cover in grade 11. So luckily this is just a little bit of a refresher video. I'm going to try not to spend too much time talking and let you get to the homework. Following along in the schedule, we're in lesson 1. There's actually 2 sections here, 2.1 and 2.2 in the textbook. As usual, take some notes, try some sample problems, some of which I'll go over in this video. There's a new course pack which just picks up where the other one left off, so pages 13 and 14 have a little bit of work for you. Some demos in class as well as some problems to try. We're going to play some games which help you to see Newton's laws in action. And there's a video that I'm going to show you in the video here, so a YouTube video within this YouTube video, and that you can also take a look at home. After class, a little bit of homework questions to try, and make sure you check out this demo called the force board in class to help you simulate some of the questions that we're going to use in this problem. More on that when you get to class. Also in this video, I'm going to start referencing the learning goals and success criteria, a PDF that I'm going to send out to you on a regular basis at the start of each unit. So for lesson 1, the learning goals, so this is what we're actually learning, as I mentioned, free body diagrams and how to analyze the forces acting on an object, and then how to use Newton's laws to describe the resulting motion of those objects. So by the end, what are the success criteria? What should you be able to do? You should be able to draw those free body diagrams that show all the forces acting at the correct angle and hopefully with approximately correct lengths or magnitudes. And you should also be able to use at least one, preferably more, of Newton's laws to describe why an object is doing what it is doing. All right, without further ado, let's get started. So a refresher from grade 11 about some of the different forces you're likely to encounter when you're analyzing motion in grade 12. They're the usual suspects, for example, the force of gravity, the normal force, tension forces, various friction forces. Here's a new one, air resistance, or what we've also been calling drag. And of course, the good old, quote, applied force that everyone seems to use all the time whenever a person is pushing or pulling on an object. So just to go through these a little bit, as you know, the force of gravity is a force that acts in the downward direction toward the center of Earth. More specifically, it acts between the two centers of the objects we're talking about. So if you happen to be standing on planet Earth, sorry, I drew a little oval Earth there, and if you happen to be not at the pole region or at the equator, but here, let's say somewhere in the middle, well, the force of gravity for you would be straight down toward the center of Earth, because of course the center of Earth being here and the center of you being right here, the line joining you two would be the direction along which the force acts. And we're going to learn more about the force of gravity and what determines its strength a little bit later on. But my point here is that down for someone on this side of the Earth would not be the same as down for someone, let's say, on this side of the Earth. And so, of course, down over here is this way. So you have to keep that in mind. But usually we're talking about flat ground, for example, a classroom, where down is just what you normally think of as straight down. The normal force, remember back in grade 11 you learned about the normal force. I don't know if your teacher mentioned to you that in math, the word normal often refers to perpendicular or 90 degrees. So when we say the normal force, we're talking about a force vector that is 90 degrees or perpendicular to something. The question is what? And the answer is the normal force acts perpendicular to the surface that an object is situated on. So keep in mind with the normal force, an object must be in contact with a surface for there to be a normal force. For example, a ball thrown in the air, there's no normal force acting on it. However, a car on the road definitely has a normal force. A common mistake I see is for people to include the normal force in every analysis of motion, and this is not necessarily correct. Tension forces, for example, the tension in a string or the tension in your arm when you are holding up a bag, for example, to carry it home from the grocery store. This is an interesting force, which I'll talk more about shortly. However, for the most part, we're going to see tension in strings that are exerting a pull on some object. And keep in mind that the tension force acts along the length of the string. So if you can imagine the string in the question, then you'll be able to figure out the direction of the tension force. Friction forces, of which there are fully 4 mentioned in this chart, which, by the way, this chart, Table 1 in Section 2.1, is out of your textbook, Physics 12 by Nelson. I want to give credit where credit is due. This is not my chart here. The friction forces, FF, just as a general symbol, FK for kinetic friction, that's the sliding friction that you learned about in grade 11. If something is sliding past something else, for example, you are dragging a box across the floor, you're encountering sliding or kinetic friction. Static friction, or what I sometimes like to call sticking friction, this is the idea that sometimes you push on an object and it doesn't want to move. For example, if you put a brick on top of a table, let's say, and you give it a very, very slight push, it won't budge even though you're pushing on it. That's because it's sort of sticking in a way to the table, and we call this kind of friction static friction, the friction that prevents slipping. Air resistance and drag, look back to an older video that I made on this, section 1.3 in the textbook. We talked all about drag, so I'm not going to mention it here, except one thing I will talk a little bit about here is that all of the friction forces tend to oppose motion. So if something is moving and there is friction, look for a friction force to be drawn opposite the motion. And finally, the applied force. I guess any force could be considered an applied force. For example, gravity is just the Earth applying a force on you down toward the center. The engine of a car applying a force to turn the wheels, and the wheels subsequently pushing on the ground, and the ground subsequently pushing on the car to make it go forward. Another example of an applied force. Or maybe it's just you pushing on something. So applied force is kind of a catch-all term. You've got to be careful when you use it. Sometimes we can be more specific than just saying applied force. Okay, so here are some of the ones you're going to encounter. Let's talk a little bit about something that's probably a bit more exciting, the fundamental forces. This chart here I took out of Wikipedia under a title or an article of the same name, Fundamental Forces. And allow me for a moment to try to convince you that even though there's a big list of forces here, they actually all fall into, believe it or not, all of these fall into one of 2 categories that physicists have sort of figured out over the years. Gravity is its own force. So if we take gravity here, it obviously down here goes into the gravitation row. Never mind about this current theory explaining it. This is something for you to look into if you want. I'm going to skip it for now. Leave mediators alone for now, but take a look at this, the relative strength. We assign gravity, which by the way is the weakest of all the forces we know of in the universe, we assign it a relative strength of 1, and then we look at how these other forces compare in strength, and you can see they just blow gravity right out of the water. Gravity is by far and away the weakest force. More on this in a moment. Long distance behavior. Can you think back to when you studied gravity in grade 11 and you learned a formula that looked like this? G m1 m2 over the distance between the 2 objects squared. Well, they just use the symbol r here, but it's the same thing. They're trying to tell you that the ultimate behavior of this force is such that as you increase the distance, you're increasing the denominator in this equation, and therefore the force is getting weaker. How is it getting weaker? As 1 over the distance squared. So that's what this column here means. What is the range? Gravity acts at infinite range. So believe it or not, even as you sit listening to this video, a quasar galaxy billions and billions of light years from Earth is actually exerting a gravitational force on you right now, even though it's so far away. Not all forces are like this, and I'll explain that in a moment. Now let's take a look at some of these other forces. For example, let's start with the tension force. Think of the tension in a string. Take a string if you have one now, or a cord or something, and pull it. It doesn't want to be pulled apart. It's as if something is holding it together. Well, if you think a little bit about it, what's holding it together is the bonds between atoms and molecules within that cord or string. And if you think back to chemistry class, what is it that holds atoms and molecules together? It's those, covalent bonds or ionic bonds or whatever they call them. I don't know, my chemistry's not as good as it used to be, but my point is, it's the attraction between the electrons and the protons in the nucleus, the electrons in the electron cloud in the nucleus of the other atoms that holds things together. These, if I remember from my chemistry days, are what bind atoms into molecules and lots of molecules into larger structures. So would it be safe to say that tension is actually just one example of what we call the electromagnetic force? Electromagnetic referring to the electric attraction of opposite charges. For that matter, look at the normal force. The normal force is the force that's holding up your laptop right now as you keep it on your desk as you watch this video. Why doesn't the laptop crash through the table and fall to the floor below? For that matter, why don't you, sitting on your floor, crash through and fall down underground? Well, it's because the table in the case of the laptop or the floor in the case of you in your chair are strong enough to prevent you from doing this. Well, what does that mean? Once again, think of the subatomic structure of these surfaces. There are atoms within which there are protons and electrons, and they are attracting one another. And if they do it very strongly, then you have a solid table. I'm going to hit the table right now. You can hear that. That's a pretty strong table. The bonds within it are strong enough to prevent my laptop from crashing through. So the normal force is really just a type of electromagnetic force. And for the friction forces, I'm going to leave it to you to think about why these also might be examples, in fact are examples, of the electromagnetic force. That would be a good thought experiment, or not a thought experiment, but a student exercise for you to go through. Figure out how friction is also an example of the electromagnetic force. Even the applied force, if you take your hand and push on something, how is that an example of the electromagnetic force? Once you convince yourself that this is the case, let's go and look at some other details that we looked at with gravity. First of all, the range is infinite. Secondly, the formula that talks about the force of the electric force is actually, as we're going to see later in the course, it's quite similar to the force of gravity formula. You're going to see something like Fe equals, and there's going to be a bunch of stuff in the numerator, but underneath you're going to see the distance squared yet again. And for that reason, the mathematical or long-distance behavior and the range are the same as with gravity. So these two guys have the same math, but as we'll see later in the course with an interesting calculation, the electromagnetic force is much, much stronger than gravity. Okay, that leaves two forces that I haven't talked about and that I'm going to leave to you to look up because they are super interesting, maybe more interesting than the two we've talked about. First of all, let me give you a little thought. Within each atom, or almost every atom, are more than one proton, which I'm going to show with the letter P in a little circle around it. Think of all those protons in the nucleus of an atom, right? Well, what did you learn in grade, I don't know, 5, 6, 7? Like charges repel. These protons should be repelling one another and flying apart, yet they aren't. We know that the nucleus of an atom is generally stable for many atoms, not every single one, but for a lot of the ones around you, they're quite stable. For example, the desk that you have is not just suddenly decomposing or turning into some other object or disintegrating. What is preventing these protons in the nucleus from repelling? Some force must be pulling inward, and it must be stronger, so I'm going to use a longer force vector, must be stronger than the electromagnetic repulsion. Well, enter the strong nuclear force, which has a stronger relative strength than electromagnetic force. The theory that explains this is called quantum chromodynamics, or QCD, and the range is very tiny, 10 to the negative 15 meters, which explains why this only works within the nucleus of an atom. It doesn't have an infinite range like the other forces I've discussed, and that's why it's just a nuclear force, and that's all there is to it. There's one more nuclear force. It has something to do with radioactivity. If you're interested in this, I strongly encourage you to do a little bit of research because it's very, very interesting stuff. All right, those are the four fundamental forces. All of the forces you and I know about and that we talk about in this course fall into one of these categories, end of. All right, moving on, let's take a quick look. I want to speed up here and get done because actually the bell is going to go in a minute. I'm taping this between periods. A couple of sample problems in section 2.1 show you some common scenarios and the resulting free body diagram. So for example, a girl pushing a chair across the floor. Remember all this? Gravity force down, applied force forward, a little bit of friction backward against the motion, and of course the chair is on a tabletop, so a normal force, which by the way, if we extend this down to the floor, the surface, let's watch what happens. It does actually form a right angle, right? 90 degrees, right angle with the floor. That's why it's called the normal force. Here's another example that you can look at in more detail when you're done. A child pulling a toboggan up a hill. This time, the surface is inclined at an angle to the horizontal, and so the normal force, if you look at it, which goes up this way, does it follow the rule that the normal force must be normal or perpendicular to the surface? Yes, that is a 90-degree angle. Here's an example that you're not so familiar with from grade 11 of a normal force that doesn't point straight up the way it did over here in this sample problem. Remember, normal means perpendicular to the surface. If the surface is not horizontal, then the normal won't be vertical. This child is pulling the toboggan up with a string. There's tension going up. There is friction, of course. Snow doesn't have a lot of friction most of the time, but it does have some. And of course, the force of gravity acting straight down. Here we're imagining that this child is on Earth. The Earth is a big globe like that. Of course, doesn't look curved when you and I stand on it. We're much too close to the surface. But straight down toward the center is the direction that gravity would pull. And here's a free body diagram showing the angles. You might start to notice cos theta and sine theta. If you're thinking two dimensions and components, good for you. That's where this is heading. Starting in the next lesson, we're going to look at analyzing forces in 2 dimensions using components. So there's a big happy face for you. Moving along, we're just going to finish up with the 3 rules that all forces follow when they are acting on an object. Newton, as we all know, is the guy who is credited with formulating the 3 rules that summarize all the things forces can do. And that's a big accomplishment, to summarize all of the motion that we can observe in the entire universe according to 3 rules. What are these rules? Just to refresh your memory, because you did these in grade 11. The first rule, or law, an object's velocity will be constant unless an external and unbalanced force acts upon it. Let's break this down. This means that things will move at a constant velocity. What does constant velocity mean? Well, since velocity has a magnitude, which is kind of like your speed, and it also has a vector nature, which is your direction, therefore, all objects keep the same speed and direction unless forces from the outside push on them in a way that they are not balanced. In other words, they're lopsided, more pushing in one direction than another. If that situation arises, then the speed and or direction will change. Can you think of some examples of where you push in a lopsided way on an object from the outside, externally, and as a result, its speed and direction changes? Here's another one, his second rule, or second law, that the acceleration of an object depends on the net force acting on it, which is another word for unbalanced force. There goes the bell, I have only a few more minutes. Divided by the object's mass. If this sounds a little wordy to you, maybe the equation form of the law will refresh your memory. Remember this? A equals F net divided by M, or some of you prefer F net equals ma. This is the mathematical version of Newton's laws, and we will study it in much more detail when we get to the next lesson where we actually apply it quite a bit to many different situations. In fact, this is pretty much what the whole unit is all about. However, all it's telling you is that when you apply an unbalanced force on an object, a net force, it will accelerate. That is, it will change its speed and direction. How much will it accelerate? Well, the more net force you give it, since this is in the numerator, therefore the more acceleration you'll get. And conversely, the heavier the object is, the larger the denominator will be, and therefore the less acceleration you'll get. Can you think of an example of this? Think of the game of rugby. I know the boys and girls rugby teams are playing these days, so let's think about them. they want to accelerate the opposing players away from scoring. So what do? They apply as much force as they can on these guys and girls, and hopefully they redirect them with lots of speed away from scoring. However, it's difficult. The more massive the other player is, the larger the denominator, the less acceleration you get, and therefore you need to push harder or get a few more of your buddies to help tackle the other person. All right? There's Newton's second law relating to Thornley. And I finish off with Newton's third law, which says that when object number 1 pushes on object number 2, and with a force that we're going to call F1 on 2, object number 2 will push back on object number 1 with a force that we will call F2 on 1. These forces have equal magnitudes, but they are in opposite directions. And so a way that we sometimes write this is that F1 on 2 is equal to F2 on 1, but in the opposite direction. So the negative sign here. Can you think of an example of Newton's third law? Well, I'll give you an example. This winter it's going to get snowy and icy, and maybe your car is going to get stuck on the ice. And so someone's, your father or mother is going to say, get out and push while I drive. So you're going to get out and you're going to push. I'll try to draw a car. I'm not very good at this. Here's the car on the road. You're going to get out and you are going to push. And it's all ice down here. Well, maybe if you're lucky, the car will actually go forward. But can you predict what will happen as you push forward? Since your feet are on ice here, you're actually going to slip backward a little bit. It's kind of strange. You're pushing forward, yet you're going to slip backward. What's pushing you backward? It's the car. You are object number 1, and you are pushing the car, object number 2, forward. But the car, object number 2, is pushing you, object number 1, in the negative direction backward. Newton's third law for you. And I leave you with the following, which is a challenge to go watch this video here, Shuttle Astronauts Weightless in Space. It's in your homework schedule. It's a great little video. I'll play it as I finish off here. See how many examples of Newton's laws you can detect in the video here. For example, they are loading supplies, and apparently other humans, onto the space shuttle, or the International Space Station as the case may be, and they are, just to go back there, you see that when they give a push, due to the apparent weightlessness of these astronauts and objects, the object that has just been pushed moves in a straight line with a constant speed until it bumps into something. In other words, it's obeying Newton's first law. So this is a good example here of Newton's first law. Unchanging speed and direction until forces, this guy here, acts on them. And there are many other examples of Newton's laws. If you go back, you'll be able to detect them. All right, folks, thanks for watching. I will see you back in class, and in fact, that's where I'm going right now to start a class. Thanks for watching. Bye.